if part of the graph or some sequence of graphs has low probability under our model, that's interesting. That tells us that perhaps there's an anomaly here or some sort of other kind of interesting thing that deserves additional focus. So this framework overall, this is the sort of the general approach that I take to thinking about data from complex systems, but especially from networks. I think it has a lot of nice properties, and I'm going to give you some examples of how we can use this in this talk. Before I do that, though, I have to tell you a bit more about how we define these distributions. How do we define this and unpack it so we actually apply it to a network? The major themes of this work are many. Learning with auxiliary information is something I've gotten interested in the past few years, mostly since coming to Colorado, mostly because when you get past a network these days, it's not just a set of edges. It's not just a set of the pairwise interactions. Instead, you often know something about either who's interacting or the character of the interaction. And being able to absorb that information into the probability models can be technically difficult. So trying to extend the models to allow us to learn with that is a major effort. Scalability, trying to have fast algorithms that allow us to fit these models to very large data sets is also very important, in part because we're getting bigger and bigger data. I felt like I had to stick that term up there, even though I have no idea what it means. How big is big? I'm not sure. Model selection, which model is better? If we have two different versions of the model, two different statements about what kind of structure might exist in this data, how can we compare them? Under this inference framework, we can do that kind of thing. We can rank in networks. We can decide which nodes are important. We can deal with partial and noisy data, which is very nice, and then, of course, think about how to do predictions and figure out what's different, what's unexpected. So these are sort of the major themes. I'm going to touch on only a couple of these in the talk today. OK. So now I'm going to give you an example of sort of the vanilla version of these generative models for networks. This is called the stochastic block model. It was first invented in the 80s by a sociologist, in fact. And the mathematical sociological community worked with it for